everyone, and welcome to today's joint webinar with Microtrac discussing the production and characterization to produce CBD and THC water-soluble nanoemulsions. Before we get started, I would like to ask everyone if you have any questions at any time, please type them in the chat window. My name is Kelly McCabe, and I'm a Senior Applications Engineer at Microfluidics. I have a background in chemical engineering, and I've been with Microfluidics for approximately 3 years now. Joining us today is Tim Jochum. Tim has earned his bachelor's degree in chemistry from Texas A&M-Corpus Christi and his master's in material science from the Colorado School of Mines. Tim has garnered a wealth of knowledge from education and industry as it relates to the instrumentation for chemical analysis through physical characterization. He has been working with RGS Scientific and Microfluidics since 2010 and is currently working closely with numerous cannabis operations to expand their capabilities. The data for the webinar was generated by Tim to demonstrate the capabilities of microfluidizer technology using the M110P in conjunction with the Microtrac NanoWave II Q for size analysis. So I'll be starting off this presentation going over our company profiles of Microfluidics and Microtrac, and then into some applications Microfluidics does very well as why nanomaterials and cannabinoids. I'll be going through nanoemulsions and stability produced with the microfluidizer processor. Tim will be going into details of the particle size analysis and his findings through his processing that he has completed, as well as the analysis with the dynamic light scattering results produced. So Microfluidics has over 35 years of experience serving the nanotechnology industry, utilizing the patented interaction chamber technology to produce high shear fluid processors. We are located in Westwood, Massachusetts, about half-hour southwest of Boston. In 2011, IDEX Corporation acquired Microfluidics and grouped us together with Quadro Engineering, Fitzpatrick, and Matcon to form the Material Processing Technologies platform. Microfluidizer processors are used in research and development, manufacturing environments, producing critical results for many applications from pharmaceutical, biotech, nutraceuticals, cosmetics, chemical industries, and so many more. We have vast application and design experience to help our customers achieve their successes. Microtrac has been an innovator in particle characterization for over 45 years. Headquartered in Pennsylvania, Microtrac is owned by subsidiary Nikiso America. Microtrac's product offerings include various particle size analyzers, including techniques such as laser diffraction and dynamic light scattering. So here are a few things that Microfluidics does very well, including nanoemulsions that can be easily sterile filtered, as well as liposomes. We have great experience in polymer nanoparticles, as well as cell lysis for the biotech applications for high protein recovery. We are very good at deagglomerations and particle size reduction in molecular weight reduction of, for example, of polysaccharides. Here below are a few of our microfluidizer processors that we offer, from low volume benchtop lab machines that can be scaled linearly to production scale. So there are hundreds of different cannabis strains and over 100 different cannabinoids. Two of the more commonly known cannabinoids include CBD and THC. THC produces the euphoric effect with some therapeutic benefits, while CBD offers a wide range of proven medical benefits such as anti-inflammatory, antioxidant, anti-anxiety, and many more. These chemical compounds, however, have low bioavailability and low solubility due to their hydrophobic properties. They can be administered in a variety of ways, including inhalation, ingestion, transdermal, and so on. In this industry, it is commonly referred to that companies are producing these CBD and THC soluble emulsions. However, this is a common misconception. And what is actually happening is that these companies have decreased the droplet particle size so small that it gives the appearance that these oils have been dissolved in the water. Solubility does not change based on the particle size. So why nanomaterials? Nanomaterials have been proven to increase bioavailability. And what is bioavailability? Bioavailability is defined by Science Direct as a measure of the amount of an administered dose that reaches the bloodstream. We do not have any clinical data, but several of our contacts who have ingested THC nanoemulsions indicate that the difference between a normal beverage and a nanoemulsion is night and day. The release is instant and the effect is potent with a smaller dose. Therefore, it's pretty easy to say that nano-sized materials can allow enhanced penetration and delivery to target site, hence increase absorption and exposure. So here you can see the importance of the nanomaterial uptaking to the bloodstream. This graph is showing that the THC levels in blood serum after inhaling have a much greater response in a much shorter amount of time than through normal ingestion methods. Actually, as you see here, the ingestion, in order for it to start taking effect, it can take up to hours to really start feeling it. And the levels that are uptaken into the blood serum are a fraction that is done through inhalation. So the improvements in kinetic solubility, or the rate of dissolution, should be responsible for the improved bioavailability of, in this example, is CoQ10, but this concept can still be applied to the cannabis industry, where smaller particle size droplets of the oil phase will result in the increased bioavailability and uptake. So when you think nanoemulsions or emulsions in general, you kind of want to think of like salad dressing, oil and water. They don't really mix. It's two immiscible liquids that are mixed together, and one phase is finally dispersed in the other. There are multiple kinds of emulsions, such as oil and water, water and oil. You can have a double emulsion, and each of these nanoemulsions they do require surfactants, which stabilize the emulsions, decreasing the surface energy between the two liquids. Oil and water nanoemulsions are used for delivering water-insoluble actives, such as these cannabinoids. So some advantages of nanoemulsions, they have greater stability, and hence the shelf life of the product improves drastically. It requires much less surfactants to stabilize the emulsion. They have the ability to be optically translucent or transparent below a certain particle size range. And this is really ideal for a clear product, such as a beverage. Nanoemulsions are scalable with the microfluidics technology as well. So how do you make a nanoemulsion? So really it starts with creating a good crude emulsion. You're basically the premix before you process it through a high pressure unit, such as the 110P here. Where you want to start is mixing a water with your surfactant, and then you're going to add your cannabis oil and, if desired, your carrier oil. You're going to use a high shear mixer to premix this, such as a rotor stator, and then you are going to put it through the microfluidizer processor. Actually, the machine you see here is the M110P machine, and this is actually the machine Tim used to perform all his tests, which he'll go over shortly. There are 4 primary and highly important parameters that can be varied with the microfluidizer processor to achieve a variety of particle sizes and distributions. These parameters include pressures up to 30,000 psi, The type and size of interaction chamber can vary, as well as what temperature you're running at and the number of passes. Okay, so to have a stable emulsion, the more uniform the particle size, the better it is. Nanoemulsions are kinetically stable, and producing a nanoemulsion with a narrow size distribution will assist in achieving long-term stability. There are a few different ways that a product can phase separate, and for a nanoemulsion, it happens via the Oswald ripening, which you can see here on the bottom. This happens as very tiny particles and droplets are dissolved in the continuous phase and then picked up by larger droplets, where those droplets are inevitably grow. To have a stable emulsion, you do not want to have a particle size greater than 1 micron. And the more uniform the particle size, the more stable the emulsion will also be. So these are a list, or just a few surfactants that you can use to create a nanoemulsion. As I've mentioned earlier, they're used to help stabilize the emulsions. There are a variety of them that are synthetic and naturally derived that come in various colors and phases. In general, synthetic surfactants such as polysorbate 80 have better emulsifying properties than naturally derived ones. For example, normal lecithin has only 20 to 50% of the phospholipid is actually provides as the emulsification properties, where higher grade lecithin, say lecithin E80, has 80% that is actually effective. You should also keep in mind that as you decrease the particle size of the oil droplets, the surface area increases exponentially and requires enough surfactant to maintain stability. So you want to make sure that you have enough surfactant in your formulation as you process in those particle droplet sizes decrease in size. However, so surfactant plays a large role in a formulation, but it's not the only thing. Other key parameters include the ratio of oil to water, as well as even just the ratio of the surfactant in your formulation, are all key factors in a stable nanoemulsion that may require some play. So how does the microfluidizer processor really work? So this is a basic schematic of how it performs. As you can see, material is brought in through the inlet reservoir and pumped out at constant pressure. You can verify that pressure with either a gauge or a transducer. And then the real core of our technology here are those fixed geometry interaction chambers, and then material will go out through the heat exchanger. So this fixed geometry interaction chamber comes in multiple shapes and sizes, including the Y and the Z type that you see here. The Y type is primarily used for liquid to liquid only applications, such as nanoemulsions, as the two streams will impinge upon each other, forming those very small uniform droplets. And the Z-type chamber is great for any application that contains any solids where the impact zone would be up against the wall. Our equipment is great for continuous processing. It can handle very high viscosities and solid content as well. But more importantly, it also can work with a wide range of temperatures. So scaling up is super easy for the microfluidizer processor. This is one of the great advantages of the fixed geometry interaction chamber design. It's really a linear scalability. So all we really do is put these microchannels in parallel to ensure that every microliter of material is being processed under the same high velocities, shear rates, and impact forces from the lab scale unit all the way up to production. Yes. Oh, sorry about that. Okay, so to summarize, microfluidics technology is unique by utilizing constant processing pressure through a fixed geometry interaction chamber. This chamber, a fixed interaction chamber, is put in, the microchannels are put in parallel to scale linearly from the small scale to production. And you can work with very small volumes all the way up to very large volumes and provide excellent batch-to-batch repeatability. Microfluidics technology is also CGMP compliant and has clean-in-place and steam-in-place capabilities. This is a quick overlook of our microfluidics product portfolio, which offers a wide variety of microfluidizer processors, which includes several lab machine designs, as well as a couple pilot scale and production machines. At Microfluidics, we value serving our customers and offer various applications and lab support by providing different tests. We work hand in hand with our customers to perform proof of concept, process optimization, and scale-up tests to ensure your satisfaction and reach your product goals. And without further ado, I'd like to pass this presentation off to Tim. Thank you.
Thanks, Kelly. So I'm going to talk about dynamic light scattering the Microtrac way, and then step into the nanoemulsion processing that I did. But let's go ahead and start off with dynamic light scattering. So these are the three main rules when it comes to dynamic light scattering. The particles have to be dominated by Brownian motion of the matrix, which means whatever liquid your particles are in, that liquid has to be imparting motion on the particles. And the velocity of those particles is directly related to their size. Big particles move slow, small particles move fast. And that's the general principle when it comes to dynamic light scattering. All of the light scattered from those moving particles is what we use to generate our particle size distribution. It is a great solution for anything from 4 to 5 microns down into the sub-nanometer range. Here's the basic principle when it comes to dynamic light scattering. The laser goes in, interacts with the particles, and that shifted light, that interacted light that comes back is measured by the photodetector and then transformed into the output. There's two different ways that you can compare the reference light to the shifted light from the particles. And one is a reference beating method where a portion of the reference light is used specifically as a comparison. And the other one is a self-beating method where you're trying to gather all of the light, the reflected light as well as the shifted light from those particles. Using the reference beating method, you can get much, much higher signal to noise ratio than you can with the self-beating method. The way that Microtrac deals with their probe is basically an optical fiber transmits the laser light into the sample at a specific point. But beyond that, Microtrac decided that it's a good idea to make sure we got a probe tip on the front with a specific window that keeps the focal point just inside the material when it comes for the analysis point. That's better shown in this slide here, where you can see the focal point of the laser is just inside into the suspension around 50 microns. And here is a graphic you can see where that some of that reflected light, around 2%, is what we use as our reference signal. The easiest way to describe it is when you look out a window, you can still see your reflection in the window, but you can also see what's outside. That reflection is what we're using as our reference signal. The reason why we do it that way is because we want to, it boosts the signal, but the benefit of boosting that signal is we can get a much higher wide range of volume percent analysis capable of that. So we only care about the light that's coming directly back at us, 180 degrees. So the particles that move toward us and the particles that move away from us, those are the ones that shift the laser light red or blue. The reason why we do it that way is we don't have to pass through the sample, and risk multiple scattering events to get a good analysis of the product. That's the reason why we can get up to 40% volume percent measurement. Now we've got this graph here is a silica sample that we diluted over and over and over again to show that we can go from a very high concentration of this material to a very low concentration, and we don't see a change in that particle size through the dilution curve, essentially. And this is all back to that that controlled reference method that we use. Once we've gathered the data, now we've got the signal, the algorithm takes over. So we've taken our raw signal and it's gone through a fast Fourier transform, linear frequency power spectrum to produce these sort of lines from top left down to bottom right. And when we log frequency those curves again, instead of having lines that we've got to deal with, now we have curves that have an actual inflection point that gives us a much better analysis when it comes to separating out large particles versus medium particles versus small particles. This is just to show that the software goes through an iterative process to make sure that it's producing the best analysis possible. We can go into this much more depth, but I think it's easier if we just say the software takes care of it for you, and it does a very good job of minimizing the error. This slide here shows, so as the world is not perfect, there's going to be a bimodal distribution in any sort of your particle size analysis until you get to a certain point, and our software is more than capable of analyzing that. You can see we've got 4 different curves here, one with just 300 nanometer up to one that's half and half, 300 nanometer and 15 nanometer. And even as you start to see the increase in the concentration of the smaller particles, the software can respond to that and produce an analysis which is appropriate. So that's dynamic light scattering, the Microtrac way. Dynamic light scattering is the measurement technology. We use a reference beating controlled reference signal from our probe. It goes through frequency power spectrum and log channels to give us the best data processing, and then an iterative convolution to minimize the error to make sure that the data that you get has is the most accurate as possible. We've got multiple configurations: in-cell, cuvette, external probe, as outlined here. The Nanotrac NanoWave II, it's got an internal well. It's capable of having variable temperature analysis on the cell itself with a Peltier cooler and heater. It's got a flow cell capability to perform titrations, and the Wave 2 is actually, with the internal well, is also capable of zeta potential analysis. The Nanotrac Flex is one of the more versatile instruments that we offer for the DLS lineup. It's got an external probe that will fit into any beaker, any vial, any test tube, as long as the opening is large enough that we can get our probe into it. The Wave Q is a great tool when it comes to quality control, in my opinion, because you can line up samples from, get a very high throughput of cuvettes, and just one after the other, cuvette, cuvette, cuvette. And convenient enough, this is the one that I used for my analysis, which you're going to see here in a couple minutes. Or right now, actually. We're going to jump into the nanoemulsion processing. Again, I use the 110P and the NanoFlex Wave Q. And let's jump on into it. So we started with some, just, I don't want to say random formulations, some example formulations of THC and CBD. Both had the same amounts of THC oil and CBD isolate that was dissolved in an MCT oil. A little bit of polysorbate 80 was added, and then the rest was water. Polysorbate 80, as Kelly mentioned earlier, very common food-grade emulsifier. Nothing special, bought right off the shelf, essentially. We used the 110P at 30,000 PSI. The reason we picked 30,000 PSI is because, as convention should hold, the higher pressure at which you operate will yield smaller particle size. So we didn't mess around with 10,000, 20,000. We just jumped right to 30. I gathered samples at a first pass, second pass, a third pass, and then a final at 5 passes. And all of the samples were measured using the Nanotrac Wave II Q. And before we get the question, before samples weren't measured because the oil and water emulsion separated almost immediately. If you stop stirring it, it would immediately phase separate into an oil layer and a water layer. So a before measurement would have yielded a particle size of 3 centimeters, essentially, which is not a convenient or reliable measurement by any stretch. So the before is simply separating liquid. Let's jump right into it. The THC Nanoemulsion solution 1. As I said, when it went into the reservoir, it had to be stirred constantly, otherwise it was going to phase separate. So it produced a very wide distribution. And this is actually a good point for me to have a quick discussion about volume versus number distribution. And we were chatting about the best way to describe this earlier. And I think if you think of the solar system, right, we've got, well, I'm going to go ahead and say 9 planets because that's what I learned. But we got 9 planets, right? With Jupiter being the big guy. And if you think of our solar system in a volume distribution, the volume of Jupiter with respect to the rest of the planets is so immense that the only peak you would see would be a Jupiter peak. However, if you look at our solar system with a number type distribution, it's only one, Jupiter is only 1 out of the 9. So that would show as much less of an intense signal when it comes to a distribution. So if we apply that to our graph here, you can see the volume distribution, which is the red line, and the number distribution, which is the green line. They don't match whatsoever, which is fine. All that's telling you is we've got a very wide distribution and there are significantly large particles present. However, the majority of the particles are small. If we follow that, if we hold that convention through the rest of the talk, it'll make sense. Again, this is before the first pass, it had to be stirred constantly to keep it from separating. Moving into the second pass, you can see that all of the large particles are gone, but unfortunately, some of the very tiny particles are gone too. But we are trending toward uniformity because the volume distribution and the number distribution are starting to get closer to each other. And again, after a first pass, it didn't have to be stirred anymore because it was a much more stable solution. It was going to not separate after that point. Again, the third pass is not too much different from the second pass. We're starting to trend toward uniformity when it comes to particle size distribution. And for our first solution at 5 passes, you can see we've got near perfect agreement between the volume and the number distribution, with the number distribution being at 216 nanometers, with the volume distribution having a peak at 280. So after that, we jumped into the CBD Nanoemulsion, and we see much similar behavior. We've got a volume distribution with a wide distribution of particles, number distribution with showing you that it's the majority of smalls. Same thing, the CBD Nanoemulsion had to be stirred constantly, otherwise it was going to separate. Second pass, very similar behavior to the THC solution. We've got all the large particles gone, starting to get a good agreement between the number and the volume. That's what we're aiming for. The third pass of my CBD Nanoemulsion seemed to have a bit of a regression of the particle size distribution agreement between the volume and number. I thought it was a bit curious, but I think it's just simply because I had to dilute this one and there might have been a bit of an issue with bubbles of some sort, but I'm not really certain. However, when we jump to the 5 passes, again, near perfect agreement when it comes to the volume and the number distribution, and that tells you that it's a really, really tight distribution of particle sizes. The number distribution tells you it's around 260, whereas the volume distribution tells you it's around 316. At this point, we said, think about it. What do we do? What really affects the particle size distribution? We know that changing the pressure does, but we're already at the max of that. We know that changing or getting a higher shear interaction chamber also will give you a reduction in particle size, but we already had the highest shear chamber we could do. So the thing that gives you the most control and flexibility when it comes to particle size distribution is changing the formulation. So we did just that. We cut down on the MCT oil and we increased the polysorbate 80 concentration a little bit for both THC and CBD, ran through it one more time, holding everything else constant. And what we see in the THC Nanoemulsion, same behavior for the first pass, had to stir it constantly, otherwise it's going to separate. And first pass gives you a wide distribution of particle sizes by volume, but a majority of them are small by number. Much similar behavior when it comes to second pass. large particles are gone, smaller particles dominate. Pass 3 wasn't a very big noticeable difference from Pass 2. And when we look at 5 passes, the final solution for our second round of THC, we see we've got a much smaller particle size distribution when it comes to number as well as volume. The agreement isn't as good, but we do have a much smaller distribution. And because we haven't seen a huge change between third pass, fourth pass, and fifth pass, that tends to believe that we're not going to see that much of a difference from this point forward processing it anymore. With the CBD Nanoemulsion second round, we saw very similar behavior to the THC, wide particle distribution first pass. Moves to the second pass, most of the bigs are gone. Now we're just dealing with small ones. The third pass, fourth pass, and fifth pass, of course, or to the fifth pass, we see not much change after that. The small, by volume, we see 67 nanometers, or I'm sorry, by number, we see 67 nanometers, and by volume, we see 100 nanometers. Again, it is not as tight a distribution as it was with the first formulation, but it is significantly smaller. At this point, we said, you know what, maybe we should try a blank without active ingredient just to make sure we're doing everything properly. So this is just MCT oil with polysorbate 80 and water, so no active ingredient whatsoever. Same behavior with our first pass, wide distribution, dominated by small particles. After the first pass, again, didn't have to be stirred. Majority of the small particles, we still had a couple large particles in there. When we get down to the third pass and into the fifth pass, we see we've got a majority of the particles with a number distribution at 42. And despite the fact that it's a much wider distribution, we've got a sort of the peak around 65 nanometers for the volume distribution. To throw all that, actually, before we throw it all into a table, the comparison of the individual passes, I think, is the most telling when it comes to the data. Despite the fact that our first pass looks like a jumbled mess, we've got a volume distribution on the left, number distribution on the right. First pass is messy, so we move on to the second pass. We can start to see that there's a little bit of a separation between two of the lines and two of the other lines. We'll go down to the third pass, and now it's getting to be a bit more clear. We look at the 5 passes, you can clearly see our formulations 1 and 2 are the red and the green lines, whereas the yellow and the blue lines are formulation 3s and 4, and the pink one is our blank. So you can clearly see that formulations 1 and 2, formulations 3 and 4 give you vastly different particle sizes. And again, all we did is tweak the formulation a little bit. So showing you that that formulation change is what gives you the change in particle size. That's the best thing I can stress to you. Putting all of it in a table, that really sort of wraps it up. You can see particle size distributions in 200, 300s for solutions 1 and 2, solutions 3 and 4, down into the 50s to the 100. So we're seeing almost a third reduction in particle size just by tweaking the formulation a little bit. So the conclusions that we came up with, using the 110P, we can produce a nano-sized emulsion at 30,000 psi with either THC or CBD as an active ingredient, polysorbate 80 as an emulsification agent, right? Solutions 1 and 2 with 5 passes required to make a uniform distribution, whereas solutions 3 and 4, pass 3, pass 4, pass 5 sort of gave you very similar results, and it was not going to change much more after that. The first pass of the solution created a sort of a fraction of very small particles, and those went away the more that you process the material to get you a much more uniform particle size. And of course, the blank emulsion was comparable to the solutions in 3 and 4 because that was the recipe we used, and we didn't see any major difference with having active ingredient versus not having active ingredient. One of the things that I don't have in the conclusion, but I do really want to stress is solutions 1 and 2 and solutions 3 and 4 visually look exactly the same. So without the benefit of having that particle size analysis equipment, you wouldn't know whether you're going in the right direction by changing your formulation or not. So that having both pieces of equipment, being able to make the nanoemulsion as well as being able to analyze the size during your development process is critical. So with that, just like to thank everyone for attending. Thanks to Microtrac for using their analysis equipment, the Nanotrac NanoWave II Q. Thanks to Microfluidics for letting me use the 110P to do this work. And with that, I'll hand it over to Claudia, and we can answer any questions that come out.
Thanks, Tim. Yeah, we got a few questions, and feel free to keep submitting any more if you think of anything. So our first question is, how scalable is the process?
I'm going to take this one. The microfluidics technology is very scalable. I kind of went over how all it really is putting these fixed geometry interaction chambers in parallel, and that's how you scale. The key importance factor that you want to take away from this is that if you have a set condition on any lab scale unit, those translate directly to the production scale. So if you're running at 30,000 psi through an F12Y chamber for 2 passes, those will be the same exact processing conditions on any of the production units. So I would say it's very scalable.
Great. So our next question is, how stable is the nanoemulsion?
I'll take that one, Kelly. A nanoemulsion in particular, as Kelly mentioned during her talk, once you get below a specific size, it will be stable. The big thing that you need to understand is it's not particularly the size that creates that instability. It's the uniformity of your particle size distribution, because big particles will want to gobble up the small particles. And anytime you get gobbling of small particles, you're trending toward instability.
Thanks, Tim. So for our next question, what is involved in the cleaning and maintenance of the microfluidics machines?
I'll take that one, Tim. It's a good question. So all machines have the capability of doing clean in place. You can run water, a detergent, alcohol through it to clean it. It's really up to the customer for their cleaning protocols. We can make we can do some sort of recommendations, but we won't ever say this is it, because it's a lot of formulation dependent and what they are actually processing. We recommend a PM service annually just to clean up the machine and make sure everything is running smoothly. Maintenance is super easy. Takes mainly cleaning and then changing out a couple pieces here and there every once in a while, but that's pretty much all it is.
Great, thank you. So what are the options for green label surfactants or emulsifiers?
Yeah, I'll take that one also. And I also saw the question of what does green label or clean label mean? And that's really a consumer-driven movement that's happening right now, where everyone is going from they don't want any synthetic chemicals or any artificial ingredients in there, so it's everything that is naturally derived. I went over a few of them. So some of them include Q Naturel, vitamin E, PGS, lecithin, and things like that. It's really, there's more out there. These are just the most common ones that I've seen so far.
Thank you. And what are the advantages of other technologies for creating water-soluble CBD?
I can answer that. So the advantages you get from a microfluidizer over other technologies is we are using a pure mechanical process to reduce particle size. The microfluidizer doesn't impart any sort of particles or side effects onto your solution, providing a pure formulation. So there's nothing that's going to be introduced into your formulation by running it through the microfluidizer. And if you're trying to do a chemical method to change the solubility of these CBD or the THC, you're physically changing the chemistry, and as long as you can justify that that doesn't have any effect on the behavior of the material once it goes into the body, that's fine. But we don't have to worry about that because there's nothing happening chemically with your solution. It's just getting reduced in particle size.
So a couple of people were concerned about the effects. So will this process degrade the CBD or THC by heat or cause any other effects due to the extended runtime?
I think I can answer that as well. I haven't seen any degradation of the CBD or THC. As with any mechanical process, when you're providing work on a system, you're going to introduce heat. The benefit of the microfluidizer is that you get, as soon as it leaves the high shear interaction chamber, it goes through the cooling coil or heat exchanger to remove that heat. And I've not seen any reduction in efficacy or behaviors by simply introducing the small amount of heat that happens.
Thanks, Tim. Okay, so Tim, this question's for you. Was the particle size distribution measured again after a period of time to demonstrate stability?
Ooh, you know what? It hasn't been, but you know what? I still have the formulations, so I'd be more than happy to analyze them again, and we can include that data with the webinar when we send it out.
Great, and as a reminder, we will be sending out the webinar tomorrow. The recording will be on both Microfluidics and Microtrac's websites, as well as the YouTube channels and everything. So, okay, we have a couple more questions. So, someone wants to know what factors contribute to breaking the nanoemulsion.
I'm going to assume that you're asking what factors contribute to creating the nanoemulsion, because if you're asking me what breaks the nanoemulsion, that would be what causes a degradation or phase separation. And what we talked about, oswalt ripening is the main breakdown when it comes to phase separation or instability. If you're asking what are the main factors that go into creating the nanoemulsion, it's simply mechanical shear. That's it.
Okay, we've got quite a bit to go. What factors are you considering when you talk about the stability of nanoemulsions?
Kelly, you want to take that?
Yeah, so there's a few different parameters. A lot of companies use zeta potential. Obviously, particle size, if you see an increase of particle size over a given period of time, that shows you that it's no longer stable. Yeah.
I think that slide that you showed earlier that showed the different methods of size degradation, it was pretty evident.
Right.
Tim, you might know this. Will we have to dilute distillates to less than 40% cannabinoids with the solvent or surfactant for detection with Microtrac NanoWave II Q?
So you would dilute it with simply with water. If you're making an oil and water emulsion, to get it below the point where the Wave Q wants to detect it, you'll need to just dilute it simply with the water.
Great, thank you. So Kelly, how does microfluidics technology compare to other nanoemulsion equipment like sonication?
That is an excellent question. We actually get that quite a bit. From what we've heard from a bunch of customers and others, Sonication it has a ton of heat generation at the probe. It's ununiform processing because it's, if you think of a beaker full of material, your sonication is the probe in the middle, and you're really only processing through there, so it's uneven. Your particle size and distribution changes quite a bit. And on top of that, we've been informed that there's contamination from the sonicator, where bits of the probe, especially titanium, breaks off from it. And that can actually even lead to a taste difference as well, besides the whole contamination issue as well. And you don't really get that with the microfluidizer processor. Our interaction chambers are made out of polycrystalline diamond or ceramic, so they're very hard materials, and you won't see those particles in your formulation. So microfluidics has much more uniform processing with constant pressure, the fixed geometry interaction chamber, and you're not going to see that any contaminations, and it's very uniform, small narrow distributions with the microfluidics technology rather than the sonicator.
Great, thank you. So I'm not sure if either of you will know the answer to this, but are there any surfactants that don't taste extremely bitter? This is an important concern for beverages.
Yeah, I'm this one. I don't have, well, I guess not. I don't have the names off the top of my head, but I can definitely reach back later and get that information.
Yeah, we'd be happy to answer any questions that maybe, like on the Microtrac side, we have our PhD Phil Plants who would be happy to answer any more, like extremely technical questions. And we have all this information, so we'll be able to reach out afterwards. Let me look for a couple more questions before we have to wrap up. So, what can be reported on particle size, or maybe they're asking what's important to report? Is it percent volume, percent number, or percent intensity?
So this is the ever-present question when it comes to volume versus number distribution, right? It's my opinion that you need both of those numbers to give you the whole picture, right? So if you go purely off the volume distribution, you may be fooled by having the small fraction of large particles in there to show you that the particle size is way bigger than you think it is. But if you go off purely the number distribution, you're going to miss the fact that you've got some large particles in there that might lead to instability. So it's my opinion, you need both the volume distribution as well as the number distribution in order to prove or to show the whole picture of your emulsion behavior. So neither one is particularly right. Having both of them gives you the best picture.
Excellent. And how can we ensure Brownian flow during a Microtrac particle analysis?
I'm sorry, one more time, Claudia?
Sorry, how can we ensure Brownian flow during a Microtrac analysis?
Oh, so in order for the particles to be dominated by the Brownian motion, you simply have to have no vibration, no movement of the liquid. So if you try and do a dynamic light scattering analysis while you're stirring, it's going to be completely inaccurate. So you simply have to let Brownian motion take over by not providing any movement to the liquid whatsoever.
Okay, and was there any visual oil ring on top, specifically samples with high oil to water ratio?
So I have all of the samples 1, 2, and 3 for each of my solutions actually, and I might as well just take a quick look. A lot of the first pass that I have a bit of an oil ring across the top. However, once we get into the passes 2 and 3, I don't see any of a particular oil sheen across the top.
Okay, sorry about that. There's still quite a few to go. How does the stability of CBD THC in nanoemulsions compare with microemulsions or other processes?
So in general, nanoemulsion is more stable than microemulsions. As mentioned earlier, in order for a stable emulsion, you want it really under 1 micron. Nanoemulsions, typically the smaller the size, the more stable it is a good rule of thumb. Obviously, it's going to change based on your formulation. It's really going to be formulation heavily dependent. Tim, do you want to add to that at all?
No, that's about right. I mean, one of the common misconceptions is that microemulsions are smaller than nanoemulsions, and that's also not true. It goes sort of, if you're thinking along the scale of size ranges, we've got meters, centimeters, micrometers, and then nanometers, which being the smallest is the nanometer. So a nanoemulsion will give you the smallest, most stable particles.
Okay, Tim, I believe this is for you. In your test, did you look at the effects of this process on terpenes as well as cannabinoids? If so, were you successful in creating stable terpene emulsions? I might be
Terpenes.
pronouncing. Yeah, sorry.
No, that's fine. None of the stuff that I was dealing strictly with pure THC oil and a pure CBD isolate. So I had, to my knowledge, there should be no terpenes within any of my products, and that wasn't anything that we were dealing with at the time. Room for future analysis, put it that way.
Kelly, does your equipment pasteurize, or do you have any suggestions on pairing with equipment with pasteurization equipment?
We do not, but I can reach out to some of our contacts and see if we have anyone that we've partnered in the past with.
Okay, that looks like that's it for tonight. We will be reaching out to a couple of you who had very specific questions. Don't worry. You'll hear from us tomorrow likely. But thanks again, everyone, for attending our webinar. And if you have any Microtrac specific questions, feel free to go to our website, microtrac.com, and fill out the form on our website. And I'm sure you could do the same with microfluidics, Kelly.
Yeah, absolutely. It's highly encouraged.
Absolutely. All right. Well, thanks again, everyone. Have a great night. We'll see you next time.